the trickle of people is slowing down, so I might get going in 1 minute. Just give anybody else a chance to come in. Do I need one of these, or
maybe not for the room, but for the people
on the recording
stream? Yeah, this will be better.
Cool.
Yeah, them should work. You can switch.
Okay, that's fine. I can hold this one. Yeah. For people on stream, I guess if I'm like typing, I'll have to put the microphone down, but I'll try and shout into the mic as best as I can. Yeah. Okay. Welcome. Thank you for coming to this session. I appreciate this is like a very grand title in that it's going to like tell you all of the GPU things. Like we have 90 minutes. I'm going to tell you hopefully some useful and interesting stuff, and I'm going to give you like millions of links for you to go and like learn other more interesting stuff. I think even if this was a 4-hour tutorial, we'd be here forever. So by way of a bit of an introduction, my name's Jacob. I work at NVIDIA. I work in a group called RAPIDS. We also have Sebastian here who works at NVIDIA too. So if we have questions or get stuck or whatever, we can kind of mill around and dig through what we're going through. So what we're going to do for this workshop is this is the first time I've run this, right? And this is like something new that we came up with. My day-to-day job is working in one of the engineering teams. We focus on like cloud deployment and how to use GPU, data science, scientific Python libraries, like in whatever cloud platform it is folks want to use them in. Right, so we either end up working on the libraries themselves, right? I'm a DAS core maintainer. I work on a bunch of other stuff within the like scientific Python ecosystem. And I also work a bunch on like RAPIDS libraries. I work on NVIDIA libraries, and I write tons of documentation. I spend a lot of time trying to make all of the things play happily and nicely together. Right, so a lot of the problems we have in the GPU world are kind of more packaging problems and compiling problems and education problems, really, is kind of what it all boils down to. So normally when we come and do tutorials, we either do like a here's how to use all the libraries kind of tutorial, or here's how to like get set up and get running with stuff tutorial. What I wanted to do is I want at some point to build to quite a comprehensive guide on using GPU libraries wherever you want to use them, right? That's kind of like a non-trivial thing today. So the way I've split this out for this session is I'm going to spend 40 minutes kind of doing like Python, data science-y, programming-y GPU stuff, right? Where we're not going to worry about like magic GPUs are going to arrive and we'll use those and everything will be fine. But then we're going to spend like the second half of the tutorial being like, what does the software stack actually look like? Like, how do I install all the right things? How does software packaging in the GPU ecosystem work? What do I need? What are my dependencies? How do I actually get this stuff in the place that I want it, not in the place that like is provided to me in a tutorial? Okay, so everything for this session is linked off this. If you go follow this link, this was the easiest thing I could think to type in. It's actually just a GitHub gist. It will just redirect you. So if you've not opened this yet, please either open it or take a picture so that you can all make sure we're following on the right thing. I'll give you a few seconds to either take a picture or head to there, or you can type in the gist link, but they're not fun. But in gist, there's like a whole bunch of material we're going to start off with. We'll have like a 10-minute break, and then we'll kind of follow some of the stuff that's actually in the gist, and we'll play around. So, anybody hands up? You're not quite got to the point of noting this down or taking a picture, or no? Good. Right, I'm going to move over here then. Right, this is the gist itself. First question: is this big enough on the screen? Anybody? Yeah. Okay. Cool. Right. So. Yeah, as I say, the first half of this, we're going to look at RAPIDS, CUDA Python, kind of what is this like programming environment? How do we write code for this kind of stuff? Then I put like 10-minute break, but it might just be like buffer time because I'm terrible at timekeeping with these things. And then we'll spend the next 40 minutes actually like looking at where to get the software from. So for the first part, we're going to use Google Colab. Right? It's a notebook-like environment. If you've not used it before, it gives you Python. Google will give you a kind of basic GPU out of the box for free in their free tier. So you just need to like register for a Google account. Hopefully most people can or have one of those. So we'll run through like some notebooks in Colab just so that you can get a feel for this stuff. But then in the second section, we're going to go through this other platform that we have called NVIDIA Brev, and I'll tell you a bit more about that later, but it lets you spin up VMs, right? Think of it like any other VM cloud provider-y thing you can think of. It's that. And so we're going to go through one of ours because I can easily give you credit for that, but it is portable. We're just going to play around with the Ubuntu machine and explore some of this software packaging. So what I have like two choices basically for this first part, because I wanted to get a feel for who was in the room and what kind of stuff you would find most interesting. I guess to like prefix, I don't want to stand here and talk to you for like 90 minutes. I want to stand here and like have a conversation with you for 90 minutes. Right? So please like ask questions and put your hand up and interrupt me, and if I'm boring, then redirect me. Like we can kind of jump around all over the place to whatever's going to be the most impactful and most useful to you. I also have stickers, like NVIDIA and RAPIDS stickers. So if you ask questions, I will throw stickers at you, because that always makes questions come. So in terms of material, we have two chunks of notebooks, right? One is targeted at maybe the PyData community. It's like pandas, scikit-learn. I want to play with data frames. I want to play with notebooks. I want to do a bit of machine learning, kind of stuff. The other tutorial, okay, that one starts like top down, right? It's like libraries you've probably heard of and used and know and love, and I'll tell you how we made them faster with GPUs, or how GPUs can be used to make them faster. The other tutorial kind of starts at the other end of like, what is a GPU? Did you know you can write code for the GPU just in Python? You don't need to learn C++. Here's some cool libraries that let you do that. And we start from like the bottom up and come up through like CUDA kernels and parallel programming and all of that kind of stuff. Kind of fits more into the world of you wanting to write your own custom code, or just to understand why these things are doing things the way they are, why they're fast, why they're interesting. So yeah, we've got two approaches. We can go top down through the stack, or we can go bottom up through the stack. We definitely don't have time for both. We probably don't have time for either, to be honest. We'll get partway through one of them and then switch gear. So the two things are linked here, right? So the RAPIDS community tutorial is the top-down one. The Accelerated Computing Hub Python tutorial is the bottom-up one. They both just use Colab. You only need the Colab free tier. You can run through either of these in your own time. So like all of the options are on the table. But in terms of the next kind of 30 minutes or so, let's do like hands up vote for like top-down pandas scikit-learn stuff. And then hands up for bottom-up number. Let's do some CUDA programming. Okay, good. I say good because I wrote this tutorial and I didn't write the other one, so it's a lot easier for me to teach the one I wrote. Okay, that's good. Let's start there. Let's do this then. This is kind of fun. I am going to start with a tiny bit of preamble into like RAPIDS and what we are as a group before we dig into this. But for all of you, I would click on that link that I just clicked on, so the Accelerated Computing Hub tutorial. And if you scroll down, there's just like a ton of opening Colab links for each of the notebooks in the repo. So if you can just like open the first one and make sure you can actually like log in with Google and it lets you in and whatever, we can carry on from there. And while you're doing that, I'm just going to type in RAPIDS for GitHub. Yeah, let's go to the GitHub thing. Yes, okay, this is us. This is our GitHub. So RAPIDS is like a group that mostly, it's an open source community, right? We built a whole bunch of libraries that use GPU acceleration to speed up either libraries directly within the Python ecosystem, or we add like new libraries, or we add alternatives of the same library. You can kind of find various levels of that. Almost everybody that works on RAPIDS also happens to work at NVIDIA. That's just a fact that NVIDIA is very good at hiring people out of the community, I guess. Like I worked on Dask and worked in the Python space before I worked at NVIDIA. There's a whole bunch of us now. But that doesn't mean like this is an NVIDIA like product that only NVIDIA can build, right? This is an open source community. We're very keen to like engage and have open source kind of discussions and contributions and whatever there. But this is part of the NVIDIA like GitHub family, I guess. And there's like a whole bunch of libraries in here. Some of them are, so if you've used pandas, there's this library we have called QDF, which is kind of like a re-implementation of pandas that uses the GPU. to the point where you can like import QDF and the API looks familiar. You can import, we have this submodule called qdf.pandas, which then just kind of makes all of your pandas code, it swaps out under the hood and makes all of your pandas code faster without you having to rewrite it. If for some reason our GPU one doesn't work, it just falls back to like normal pandas, but whenever it can use the GPU, it will do that. And we have this kind of for lots of things. So we have QDF for pandas, we have QML for scikit-learn, and we have the same kind of thing. We have this new thing called QML.excel, which is the same kind of zero code change acceleration. If you like NetworkX, we have like a NetworkX plugin that uses this library called QGraph for doing like graph analytics. And then there's a bunch of primitive stuff in here as well, Raft and RMM, and like other low-level libraries for building out other like GPU-accelerated Python projects. All of this is kind of focused on the PyData, SciPy kind of community in terms of tooling. Then more generically, we also have this thing that we call CUDA-Python. And so put your hands up if you've heard of CUDA or know of CUDA. I don't say you know how to write CUDA, but you know of CUDA. Right? It's this program paradigm that we have in the NVIDIA world for writing code for GPUs. Now, most people associate CUDA with C++. Right? There is a C++ language extension which lets you write code in C++ that will compile and run on the GPU. And this is like CUDA C++. But as of like last year, or in the reasonably recent past, Python was added as like a top-level language to the CUDA ecosystem, right? So anything you can do in theory in CUDA C++, you can also now do in CUDA Python. Right? You should be able to write normal Python code. You'd have to worry about C++. You'd have to worry about bindings. You'd have to worry about any of that kind of stuff. You just write Python, and then that code will be just in time compiled down into the same bytecode that runs on your GPU. And so, like, this tutorial is kind of focusing on that world a little bit and exploring some of the things in there. And you can kind of see in these notebooks as we go through, we're starting out with some basic, what is the GPU, why is it interesting, why do we write code for it, and then moving up through Number, which is the library that gives us this control of doing just-in-time compilation, and then it moves up through these libraries I mentioned, like CuPy and QDF, QML, all through the higher level things. You could then, once you get to the end of this, you could go to the other tutorial, which will give you more like applied examples of using the higher level libraries. But what I'm going to do, I'm going to start with this notebook one, CPU-GPU comparison. Hopefully it just logs me straight through. Good, okay. So hopefully most of you have managed to get to a point like this, where you're in Colab, you've got a notebook open, I'm in notebook number one, and what I want to do is I want to make sure that my runtime type, right? So if I click up in the right-hand corner, there's a little drop-downy thing, and it says change runtime type. I want to make sure I've got a T4 GPU selected, right? Go for it.
I'll stick my neck outside. I'm not in Colab because I missed the bit where you said the notebook you should be able to register now and log in and so on.
Yeah. Okay. So did you get as far as opening this one? Or did you? So from the beginning, there was this link.
Yeah.
Yeah.
And there's a welcome notebook.
Yes. There's a welcome notebook. I didn't open the welcome notebook. I must confess.
Which notebook is it?
I've opened notebook 1 rather than notebook 0.
CPU GPU comparison.
That's the one. Yeah. That's the first one that I have opened. Thank you for calling that out. Yeah, the welcome notebook, I think, is all the things I just said, so I glossed over. Right, so I'm going to drop this down and click Change Runtime Type, choose a T4 GPU. If you want to pay for Colab, then you can have other GPUs, but for everything we're doing, T4 is fine. They're kind of run-of-the-mill inferencing GPU that you can get on the cloud. And then when we run notebook cells, it should kind of connect, but I'm just going to click Connect up here as well, just to make sure that I kind of get my session. I'm going to make it a bit bigger as well. I'll get rid of the table of contents. Okay, so kind of starting from the beginning, right? GPUs are often thought about as just like this magic thing, right? There's a thing that you can get in your computer, and I install like a slight variation of my code, and then the thing goes faster, right? Because somebody else has done all the thinking of how to implement that kind of code. Now, what we're going to do here is kind of talk about why the device is different, why it's interesting, and then how, like, which problems are useful and solvable with the GPU. So when you have, this diagram kind of shows you the internal structure, a very simplified version of the internal structure of like a CPU and a GPU. So in a CPU, you might have like a few cores. You can get servers with nice lots of like tens of cores these days, but like the laptop in front of you probably has maybe like 4, 8, 12, some kind of single figure to maybe double figures number of cores. Each of these cores can do kind of sequential mathematical operations. It's got, you have assembly code that the core will step through, and basically everything you will have done on your computer will be using these cores, right? You write some code and it is executed line by line by one of these cores. That's like especially true in Python world because everything is single-threaded, and there's all the no-go stuff going on, but without getting into the complexity of multiprocessing and threading and whatever, Python is a single-threaded language today. And you just think of like one of these cores is going to have your Python code stepping through. And you have some RAM, right? You have some memory. Your code is going to get loaded into that memory. Your data is going to get loaded into that memory. The CPU is going to do some operations on that. Now, the structure of a GPU is it looks similar, but things are different shapes and sizes. So instead of having a few cores, we'll have like thousands of cores. And each of those cores is going to be like weaker. It's not going to be as fast as the CPU core, but there's a lot of them. And they can all do kind of separate operations. They can work independently of each other, but in like a coordinated way. And this is something that takes a little while to kind of get your head around, I guess. So I wrote this tutorial just after I joined NVIDIA. I joined NVIDIA as like a distributed Python person, and then had to learn all the GPU stuff. So a lot of this, you can see my like train of thought of like learning all of these various things. So normally when you write code for the CPU, you can have lots of programs. They can all be running at once. The operating system's going to handle swapping between them and like giving time on the CPU and not. On the GPU, we typically think of it as like, no, I've got all of these cores. I have a GPU, and my GPU is going to do a thing. And I'm going to write some program that's going to consume the whole device for that period, for some period of time. And I need to think about like the parallelism in my code and how I write it. Now, I think this video disappeared, which made me say, yeah, that made me sad. Let me see if I can quickly find it.
Is it the one with the volcano?
Yes, it is. I'm going to click that. I don't know why it disappeared. Right, the Mythbuster, NVIDIA hired the Mythbusters people to do a cool demo of the difference between a CPU and a GPU, and it's just kind of fun anyway. Right, but they built these two paintball gun machine things. The idea that each one would draw a picture in the same way that a CPU or that a GPU would work. So this is a CPU robot, right? It's an arm with a paintball gun on it, and it's loaded with paintballs. And let me skip through a little bit. Maybe not that far. Right, they're painting a picture of a smiley face, right, with this gun. Is like shooting one paintball at a time. This is how your CPU works. It does one operation at a time, and then in aggregate, those operations add up to be the result. The GPU is this thing that they've built, right? This is the same machine, kind of, right? It is a big paintball gun robot, but instead of being one paintball barrel that can move around and do kind of different, changes operations, it's many, many, many paintball barrels that are all connected up to one big gas tank, and they have one big button that says, like, go, do the paintball. And so the difference here is instead of having the machine change its operation each time in order to paint the picture, what they do is they set it up and they set the initial conditions of this machine. Right, and they do that by loading a different colored paintball into each of the barrels of the machine, right? But then the operation that they compute on it is just the same operation. It's just like, compressed air down the barrel, right? And everything is kind of set up in this way where you think about kind of loading data into memory and then bang, do the operation and then do something with the result of that. And yeah, I don't know, they throw some t-shirts and whatever. Let's find them actually do the thing. Come on. I like the other video because it was all like cropped down. Okay. So, I don't know, fun, dramatic effect, sirens, whatever. They hit the button and it paints a picture of a smiley face, right? Slightly different smiley face. But you kind of get the idea that there's been like one compute operation, and the initial condition of the data decided what the picture was going to be. And, you know, that's kind of fun. They show it in slow motion and all sorts again after that. But this is kind of how you think about programming for the GPU, right? So you have to set up your data in memory, and then you write some kind of operation, some kind of algorithm that is going to do a parallel operation. And then you gather your result at the end. So, one of the first questions you have to all of that is like, that sounds great, that sounds fun and interesting. Like, how do I touch this? How do I do the thing? How do I poke a GPU? I mean, this is like my first kind of set of questions, was just, this all sounds wonderful. I've imported PyTorch before and done like CUDA equals true or whatever in PyTorch, and then it did the GPU and I didn't really know what was going on. Like, how is that communication happening? So to answer that, like, I found the mental model useful of thinking, well, if I've got code on my laptop and I have a server somewhere and I want to run some code from my laptop on that server, like, how would I do that, right? I need to get my code from here to the server. So maybe I'm going to check it to Git and then clone it onto the machine. Maybe I'll just SCP it straight across. Like, I need to get some way of getting the code over there. I also need data somewhere that's going to get into that server. Maybe I'm just going to SCP that over, or FTP it, or whatever. Maybe the server's going to pull it from S3, or I don't know. It's got to go. It's somewhere else, and it needs to pull some data in somehow. It needs a mechanism to do that. And then I need some way of controlling that machine. I need to tell it, you know, Python run my script. So I would probably do that with SSH, right? I'm going to log into that machine and then run the script. There's a million different ways you could do these things, but I think having this in your mind of like, there are predetermined protocols for speaking to a remote machine. The exact same thing happens when you're talking to a GPU. Right? Is this predefined protocol for talking to it. It's just called CUDA. Unfortunately, we named a lot of things CUDA, and so it gets a bit kind of overlapping. But we have within CUDA ways of talking to the GPU. But you just think of it as the same kind of thing. It's another machine. It happens to be inside your existing machine, but it is on the end of like a network connection that's using PCI to communicate between the CPU and the GPU. But it has the same kind of makeup. It's a processor, it's got its own memory. Like, I need to think about, how do I get my code onto the GPU? How do I get my data onto the GPU? And then how do I invoke the function on the GPU? And we just have kind of methods in CUDA for doing this. And I'll show you some of this in Python in a minute. Because you can do everything directly in Python. So what I'm going to do, I'm going to close... No, I'm not. I'm going to leave this notebook open for a second. I'm going to go back to this list of notebooks and just show you. I'm going to open the first one. Right? I'm going to open notebook 2, number. So I'm going to open that in Colab. And then I'm going to click, I'm going to make sure my runtime type is GPU again. And I'm going to click connect, and it's going to say, you're not a premium Colab person. So then I click manage, and I just kill the first one. Right? I don't want that GPU anymore. It can go away. And then I can click connect and get a fresh GPU for this notebook. So if you're using the free tier, you need to just kind of juggle around what you're doing in terms of kernels. Kernel's the wrong word for that, I guess. What you're doing in terms of runtimes. Getting ahead of myself already. Okay, so the way that we can talk to the GPU, there's a few different ways of doing this, but in Python, like a very popular way is using a library called number. You might have come across number for like other reasons. Number is this library for doing just-in-time compiling of Python code into something else. Who here has used number for some things? Who here has used number for GPU stuff? Yeah, okay. A couple, but yeah, so number is kind of at a high level, it wants to just-in-time compile your code down into machine code that will run fast on the CPU. But you can give it different backends, different targets, and so one of those targets we have is CUDA. Right, so I can write some normal Python code, and it will compile down to the GPU. Now there's a couple of challenges, I guess, with writing code for the GPU. Because it's this big parallel processor, and it wants to do like these big batch operations where it does lots and lots of things in parallel, the way that we have to think about writing functions for it is just slightly different. But it's different enough that there's like new terminology that you have to learn for these things just to help GPU people talk to each other, I guess. But you'll hear quite often people talking about CUDA kernels, right? And I kind of, at first, I found that an overwhelming term because I've heard of the Linux kernel. What's a CUDA kernel? Like this is like a big word that I don't understand and need to unpack. And so like the way I would describe that initially, that helped me is just a CUDA kernel is a function. Right? That's all it is. It's a function that you're going to call on the GPU. But there's a couple of caveats that make it different from a normal function. One of the things is that it can't return. There's no return statements in a CUDA kernel. And this is because if this function is going to get called 10,000 times concurrently on a device, what is it returning? Where does all that return go? Like that could be actually quite a significant amount of data if every function returns like a 64-bit floating point number or something. Like where do I put 10,000 of those every nanosecond or however quickly my function? Like we don't wrangle the output of that. What we do instead is the kernel modifies memory directly. Right? So we give it some pointers to some things. Usually these are just like NumPy arrays, right? Or arrays that look like NumPy arrays. And we just say, here's an array that's full of data. This is your input. Here's an array that's full of data. This is your output. Like, your job is to just like read something from here and put it over here. Like, we're not going to return anything. You're just going to modify memory. You're going to consume from something and write out somewhere else. The other thing we need to do is we need to tell this function how many times we're going to call it, right? Because although the GPU can do however many thousands of things in one go, like from a programming point of view, we have like a thing we're trying to achieve, right? I maybe have a for loop that's going to go around 10 million times, so I need my kernel to execute 10 million times, right? Like I need to decide how many times I'm gonna call that. And we have some more words, I guess, to describe these things. Typically in CUDA world, we refer to this as the grid, right? A grid is just like, how big is the computation? How many times do I want to call it? Do I want to call it 1 million times? Right, my grid is 1 million. That's what that number means. But from a hardware perspective, the GPU doesn't actually have 1 million cores. It has some high number of cores, but it depends which GPU you've got. If you've got a T4, you'll have a certain number of cores. If you've got an L4, you might have a few more cores. If you go and get an A100 or an H100 or a B100 or whatever other random model name I make up, it will have some other number of cores in it. And next year, we'll make a new one with even more cores. And the year after, we'll make another new one with even more cores. And so we don't want like a one-to-one mapping between the hardware and the size of the calculation you do. So we basically want to break it up into batches. And you're just going to say, okay, I've got a grid of 1 million things. I want to do 1 million operations. I'm going to do it in batches of 1,000. And then whatever the GPU is, it will just do however many batches it can kind of in parallel. And there's some other like nitty-gritty stuff you can get into. There's some things that function calls within a batch can like talk to each other very quickly and do fancy, interesting things, and I'm not going to cover any of that because we definitely don't have time for that today, but it's interesting and you can go off down that world. Ignore the word warp as well because that's fun too, but for another day. But what you basically end up with saying is like, okay, I've got a grid, I want to do 1 million operations, I'm going to do it in batches of 1,000. How many batches do I need? Right, I need 1,000 batches of 1,000 to do 1 million operations. So this is the grid, we have our batches, we call the batches blocks. The blocks are made up of threads. But these are kind of like the number of invocations of the function. Now these words get really annoying and you'll be irritated by me saying threads and blocks and grids and whatever by the end of this tutorial, but these are kind of exact words that we use to describe what we're talking about. But usually you have to make some decision up front about what you're going to do. So for the purpose of this tutorial, given that it's like a short one today, we're just going to pick some numbers straight out of the documentation. We are going to choose 128 threads per block, I think, or 1,024, one of those two numbers. We'll find it in a minute. Yeah, a good number is a multiple of 32. And so we're going to pick a number, probably 128 or 1,000. Yeah, probably 128. As our batch size. It doesn't really matter at this moment because we're not doing any clever stuff between the batches, but we're just going to pick a number and go for it. So let's start with some normal Python and work our way into like GPU Python and do it like step by step to try and get a good understanding of what's going on here. And so the thing that I found closest in Python to the way that you would think about a GPU operation is a list comprehension, right? Hopefully you all have used and loved list comprehensions, right? You write a single line expression which has like a for loop built into it. You can kind of think of that as like a parallel operation. I have one line here, right, for I in data, right? This is it's kind of a parallel expression. Like the CPU will do this sequentially, one thing at a time. But you're kind of thinking about like, I'm going to map over this array of stuff. And this little bit of Python code here is just, I'm going to take in some input thing. I've got an array. This is just a range of 10. I've got some operation I want to do to it. To keep things simple, we'll just pass that number straight through. We won't do anything particularly exciting at the moment. But we'll just write a function that just takes in I and gives out I. And then if I write this list comprehension, I'll do foo I for I in data. I'm going to take the numbers 0 through 9, I'm going to put them through this function, and that function is just going to return them, so I'll get out the other end the numbers 0 through 9. Right. It's not particularly exciting, but this list comprehension is kind of that first step in thinking along the lines of, I'm going to call a parallel operation. I'm going to call something, I'm going to open the dictionary. That's exciting. So, let's run that. We get the numbers 0 through 9. Now, what we're going to do is we're going to take foo and we're going to turn it from a Python function into a CUDA kernel, right, just to kind of give you an idea of where these words go. So, I said we can't return anything. It's one of the rules of these functions is return. If you have a return statement in your kernel, it won't compile. So we need to remove that. We need to find out some other way. How do we get the answer out if we're not going to return it? So let's change things a little bit. We'll still have our same input data, but now let's just make an output array. We'll make another array called output. And our function, instead of returning, it's just going to do output.append. We've created some data structure in memory. We're going to modify that memory directly instead of returning. Then we do our same list comprehension and have a look at the output. And if we run that, we should get exactly the same thing again. Instead of returning I, we're just putting I in some other bit of memory that we control. Now, one thing I haven't mentioned is we can't do magical, any length you like, arrays. And we can't guarantee that these things are going to run in order. Right? At the moment, we've guaranteed that we're going through sequentially through this for loop, and so we'll get the numbers 0 through 9 in order put into our array. We kind of know that and understand that. But the GPU will do things in whatever order it wants to, right? It will just do this in batches and work its way through. And so we can't control when something gets appended to that output array. So instead of doing that, what we'll do is we'll import NumPy, and we'll make a NumPy array that is just our input numbers, and we'll make another NumPy array that is our output numbers, and we'll make it like the same length. So we have like a 10-element long array of inputs, and we've got a 10-element long array of output as well. It's just an empty. I'm just going to do zeros. Just an output array. We'll update that with stuff. And then what we're going to do is, when we call our function, we're going to take in our number, and then we're going to update something in the output. But we're going to use that number to decide which one to update, right? So when we get the number 0, it's going to put a 0 at index 0. When we get a 5, it's going to put the number 5 into index 5 of that NumPy array. We're just going to reuse these numbers for a minute. And so we have this little foo function again. We'll call that again. We should get the same thing. It's in like the rep as in NumPy clothing now, but it's the same thing, right? It's just the numbers 0 through 9 in here. And this is, I think this foo function is probably the most unexciting CUDA kernel you could possibly write, but it is technically a CUDA kernel, right? It conforms to the rules of a CUDA kernel. It doesn't return anything. It just modifies things in memory. So this is pure Python. It can run on the GPU. And to prove that, we can... Colab's telling me I'm not using my GPU well enough. All right. I know. I'm teaching. Right, so what I'm going to do, I'm going to import number. I'm going to do from number import CUDA. This is the number CUDA package. And I'm going to do some little workaround for some bug that we have, so don't worry too much about that. We discovered this bug whilst I was giving this tutorial once, which was not fun, not a fun day. But now what we're going to do is we're going to take the same code, and now we're just going to do the last little tweaks just to kind of wire it up into number. So we've still got our input array, our numbers 0 through 10, and we've got our output array, which is full of zeros, and we've got our foo function. Now, one thing we can't do is we've got to remember that this device is like another device, right? It's a GPU, it's inside the machine. It can't actually access the memory of the host system. And so everything we've done so far, we're just modifying global variables, which is, not a good thing to do. So we're going to pass these in directly into the function instead. And this just tells number, like, look, here's these two arrays. We need to make sure that when the function's called, they are available within the scope of the function. So we pass in the input array, we pass in the output array. But now we don't have our number that we're putting in instead, right? We just have this very generic function. And it's going to be called 10 times, right? We have 10 numbers. We want to call our function 10 times on the GPU. So we need each function to decide, what do I do, right? There's 10 copies of me. I'm a unique snowflake. What's my special quality? What do I do? And so we have this function called CUDA.grid, right? And it basically allows a function to say, who am I within the grid, right? You called this 10 times. What's my index? Which thread am I? And so every time foo gets called by the GPU, each invocation will get a unique number from this CUDA.grid operation, corresponding to its position within the grid. Yeah, go for it.
What's the one parameter?
Yeah, I know, sorry. The one parameter means give me this in one dimensions, because we can think in multiple dimensions and do all sorts of other fun stuff later. I really wish this was just a default, it's just one, and you could omit it, because you don't want to think about this till later, but we just have to tell it, I want my one-dimensional index, because GPUs can think in up to 3 dimensions because of gaming. And so you can do some fun stuff with indexes in that. There are some notebooks later on in this tutorial which do image manipulation, like blurring and grayscaling and stuff, like the kind of filters you might apply in Photoshop. And it's helpful to have a 2-dimensional index in that, because you can map that directly onto a pixel location. But in this case, we're just saying, what's my index in a 1-dimensional world? And all we're going to do is we're just going to say, take the item from input array at whatever my index is, and just put that into output array at whatever my index is. So we're just doing a copy. We're copying from one array to another array. And each time this function gets called, it's going to operate on a unique index within that array. So each time it gets called, it's the first one's going to copy index 0, the next one's going to copy index 1, etc. Now the last thing we need to do is, I said we need to tell it how many times to run. And so we have this little, I keep doing dictionary, why does that happen? We have this kind of slight tweak here where foo is a function, right? But because we've decorated it with CUDA.jit, it's become like a CUDA kernel. And before you kind of do your round brackets, I'm going to call my function, you need to do this little square bracket accessor thing, where you say, can you please do one batch of, dictionary, please can you do one batch of 10, right, is what we're saying here. But you use these square brackets to configure how many times you want to call it, basically. This is your for I in whatever section. But you just say your batch size is this, and I want this many batches, and then round brackets to call the function. So if I then click run on this one, number will complain at me for doing such a tiny, small problem on the GPU, and then it'll give me the same output. And so now what we've ended up doing is running some Python code, pure Python code, but it has, as we've executed it, number has taken it, compiled it down into a low-level GPU assembly language kind of thing. It shoved that down onto the GPU. It's taken our memory and it's shoved that down onto the GPU. It's executed the assembly code, and then it's taken the outputs of that and it's shoved it back into the CPU again, and then popped that number out. And so, in however many 1 second that took to run, a whole bunch of stuff happened. But this for me, when I was learning all of this stuff, was a huge breakthrough. I was wow, I wrote some Python and it ran on the GPU. That is an exciting milestone. Now let's unpack this a little bit further, because it is complaining about being such a tiny problem. So let's do something a bit bigger. Let's just make a big array of random numbers with 30 million elements in it. And let's make an output as well. Sometimes when I do this, people ask me, why are you making an output full of zeros? You can also just do empty and it will just allocate whatever memory, right? But it's maybe more efficient to do that. But it's just worth understanding. You've got an input array, 30 million random numbers. You want an output array, 30 million, nothing yet, but it will be something in a minute. Now let's do this in Python. What I'm going to do, I'm going to double every number, right? I'm going to just take each number out of my array, I'll times it by 2, and I'll put it in the output array. I'm going to do this over all 30 million elements. Let's just do this in pure Python, just to show us what's the absolute worst way I could possibly think of doing this. Maybe in any programming language. Just a really basic for loop in Python over a NumPy array. Never do this. But just to show you, it took 10 seconds to go over 30 million items in that array. Now let's do the same with CUDA. So I'll just reset my output again. And I'm going to do a little bit of maths ahead of time to just say, okay, I'm going to do this in batches of 128. How many batches do I need? Let's just work it out. How big is my array? What was my batch size? Divide those, ceiling, whatever. I work out how many batches I need. And then this is my little CUDA kernel here. So you notice it's CUDA.jittered again. Takes its input and output array. It asks, like, who am I out of these 30 million elements? Which one do I need to operate on? So it gets its index. And then it updates the output array with input array times 2. We then configure it. This is maybe slightly more readable because we set these before. So we say call foo with this number of batches of this size. And here's the input and the output. And we'll run that. And instead of taking 9 seconds, it took 300 milliseconds. Right. So that's going from like worst case scenario code to kind of novice CUDA code. Now, can anybody here, not Sebastian because he makes NumPy, but can anybody here tell me, like, is there a more obvious way to do what I did? I want to take an array, a NumPy array, and I want to double all the elements in it.
Then you just use NumPy.
I could just use NumPy, right? I could just do array times 2. That's like a lot easier, right? And when you're writing GPU code, you might get into a situation like this, where you think like, oh, I handcrafted all this magical CUDA code, and it ran really fast. It was way faster than what I had before. But then I found this other thing that's even simpler, and that happens to be even faster, right? NumPy was just 75 milliseconds to do that same operation. And this is a bit of a twisted example to show you that we had this NumPy array that started out on the CPU. We had to copy it to the GPU, double all the elements in it, and copy it back. And that copying back and forth is expensive, right? And it can bite you. If your problem is really small, like doubling all the elements in an array is like computationally nothing, right? And so the overhead of copying the memory around was not great. And so GPUs really excel in situations where you're going to copy the memory in and then do something kind of computationally heavy on it. And this is where the AI kind of stuff comes in, because like, well, yeah, you are doing lots of matrix multipliers and other operations that are computationally heavy, and then I'm going to take my data off and bring some more data in and do some heavy computation, and that computation needs to be heavy enough, right? And these little examples don't always show that. But just to highlight that, what I'm going to do, one thing we can do in Number is, instead of letting it copy the data onto the GPU and copy it back again, I can say explicitly, like, I'm going to do that now, right? I'm going to say, here's my NumPy array, like, copy it to the GPU, please, and here's my output, copy that to the GPU as well. Again, maybe don't copy a load of zeros to the GPU. You could probably ask the GPU to give me a load of zeros, or just a load of empty memory. There are other function calls that are better. But you can see now, my array is on the GPU already. I've done this manual copy just to show you, like, if we get the memory overhead out of the way, like, how fast can it possibly be? So let's now run our CUDA kernel a bunch of times just to see how fast it goes. So this has now doubled our array in 39 microseconds, right? So we've gone from 9 seconds in pure Python down to like 300 milliseconds in like poorly written CUDA code. Then down to like, what was it, tens of milliseconds for NumPy to do it, and then we've dropped down into tens of microseconds for the GPU to do it. Because the GPU, this is such a parallelizable operation, the GPU is very good at doing things like this. Each thread can just be copying and doubling numbers. It's very, very straightforward. But I've had to move my data over there, and now it's stuck over there. I've still got this array of all my doubled numbers. It's in the GPU. I need to ask, can I have it back, please? So we have another function that's called copy to host that just spits that back up here. But what you might find, as you see more people writing code like this, is actually, instead of doing something, you might write a kernel that does some operation. That's great. But a real-world application is probably going to be lots and lots of operations, right? You're going to do some big batch parallel thing, and then you're going to do some other transformation on it, and then you do some other transformation on it. I find pictures quite an easy mental model for this, of just like, I'm going to take an image and apply a load of filters to it. I'm going to blur it 20 times, and then I'm going to add a grayscale to it, and then I'm going to do like a, recolor this. You're going to have like a bunch of operations. Each of those operations can be parallelized, but the overall workflow is still like a sequential workflow. And if you write this naively in all of this and let Number do the memory management for you, you'll pay like so much memory overhead, right? Because that was fun. No, I didn't mean for it to do that. Like, if I have 3 kernels now, if I have foo, bar, and baz, and I just call them naively, I'm going to copy the data to the GPU, run the kernel, copy it back again. Then immediately copy it back to the GPU, run the next kernel, copy it back again. And then copy it back, and you've got all this memory overhead that's completely wasted. So you would, in Number, you would just say, at the beginning, copy all my stuff to the GPU. You would say, run all of the things, and then copy the output back. And this kind of thing where you're chaining together a bunch of kernels, all sorts of fun stuff can go on at the compiler level of like fusing them and doing all sorts of interesting optimizations. And so yeah, that's hopefully given you like a bit of a taste into some very low level CUDA stuff. Now I want to spend the rest of this session talking about like, I skipped a bunch of stuff. I said, let's go to Colab, I'm going to click GPU and we'll GPU. But many of you may be thinking like, well, yeah, but how do I get there? Like, from me with a MacBook now, like, how do I get to that point with the GPU and all the various horrors and things that can go wrong? So I'm going to like redirect the tutorial now into like more like Opsy, Linuxy stuff, just to get to that point. But what, if you found any of that interesting, or you want to continue your like learning journey on through that, I would encourage you to keep going through these various notebooks. The next one is kind of the one I kept kind of alluding to, this Number Lab, which, no, not that one. Is it number 2, maybe? Number Gauss. Number Gauss is the one that I find kind of interesting. I don't know if it's got the output stored. No, it doesn't. This one takes in the Number logo, and you write like a custom blur filter, and then you blur the logo. And it just kind of is quite a nice way to think about how you can use the GPU efficiently for something that is very parallelizable. So if you want to keep going, I encourage you to keep going with those in your own time. And as I said at the beginning, if we come all the way back to this gist, which has got like the bulk of the material in, there is also this RAPIDS community tutorial, which is the other way up through this stack. So if you want to come in from the pandas scikit-learn kind of level into GPU acceleration, like those are great notebooks as well, and it's all just available on Colab. Now, before I dive into deployment stuff, does anybody have any questions about CUDA programming or any of the stuff we just talked about? Yeah, go for it.
Just a quick one, although you may cover it, so I apologize in advance. If you want to develop some CUDA-based code using Python library, you mentioned something about if the GPU isn't available, then it will just by default run. So that sounds very useful for development because, for example, on the cluster that I use, GPUs are expensive. So is that a practical way of developing? Sorry if that may already be covered.
I mean, kind of. I think the context of when I mentioned that was like we have a library called QDF Pandas where you can write pandas code that will run on the GPU opportunistically if it's there, but it will just use pandas if it's not. But if you're writing this like number stuff that we've just done, like that will only run on a GPU machine. So there's like different levels you can come into this stack. I do have a slide that I can probably dig out, which is not that exciting. But we have this idea of one of our colleagues called this like the CUDA swim lanes or something. But like we have this idea of this hierarchy where at the very, very top it's like you just keep writing the code that you normally write, and we'll give you some plugins and some libraries and things that will just use the GPU for you. You don't have to worry about learning any of this stuff, like the Pandas plugin or the Polars plugin or the scikit-learn plugin or whatever. Like we'll handle the GPU acceleration. And it will run on a CPU machine, it will run on a GPU machine, like you just do you. Like that's the very top of the stack, but it's not going to give you like cutting edge performance. It's going to give you like a really nice speed up, but if you want to get like perfection out of your machine, you're going to have to like roll your sleeves up and write some like tuned code.
My motivation wasn't to avoid learning about CUDA, it was actually just to make sure the rest of the code glues together correctly before running.
Yeah. Yeah, no, I see your point. I mean, as we move down this hierarchy, like we get into deeper and deeper libraries where you end up, like where we just were was like the middle of the pack, I guess, and you can keep going down into like low-level world as well. I guess you're asking maybe like, is there a way to like emulate the GPU or get this code to run in a non-GPU environment? And that's something that we just don't support at the moment. Like if you want to develop this stuff, you have to have some kind of GPU, even if it's like a very small, cheap one, a gaming one or something. You can develop on a machine like that. and then scale it out onto the larger server stuff. Yeah, go for it.
Initially, you chose this to be 128. Why 128? Just curious.
So it was a number that the number documentation said this is a good number, right? Okay. And so I copied and pasted it. No, I mean it's one of those things where like 128 is guaranteed to work on all the GPUs because they will definitely have that number of threads. Even going back like generations and generations, you'll find that number of threads. So it's very cross-hardware friendly number to choose. It's also just a number to reason about, I guess. But realistically, you would probably set it to like 512 or 1024 these days. There's pros and cons to setting different numbers depending on the code that you write, but without spending like another 4 hours, it would take me a long time to explain why. But yeah, there's like a whole... People make a career, I think, out of choosing that number and the various magic numbers in all this stuff. Like people, you can spend a lot of time like really crafting this code. Writing CUDA code can sometimes feel a bit like writing C from the old days of like, I'm going to have a mental model of the assembly this is going to generate as I'm writing this because I really want to think about the instructions that the process is going to run. Like you can go that far in the CUDA world and these numbers can play a big part in like, oh, this thread is reading this number and it's got cached in this cache in the whatever. And you know, there's all sorts of stuff you can do in terms of optimization. But just out of the box, pick a safe number like 128. 1024 is probably fine these days. I can't remember what a lot of people used to use the like gaming cards for like playing with this stuff. And I'm sure it was like the 1080 or like that kind of generation. Like you couldn't choose anything bigger than 256 or... Like there's like upper limits on these numbers, and that's why we pick them. But there's not any particularly good rhyme or reason other than compatibility. Right. Okay. Any more questions before we go on to deployment-y type things? No. Good. Okay. Now I've probably put too much content in here as well, which is why it's a notebook and why this is a tutorial, and you can take this away and play with stuff. And so, in order to facilitate you playing with stuff, just out of curiosity. Put your hand up if you have an NVIDIA GPU in the laptop in front of you. Wow, I don't. There's more than I expected. That's impressive. Okay, you can do all of this on your machine if you really want to. I wouldn't recommend it because conference Wi-Fi or whatever, because we're going to install some big hefty packages in a second. So we're going to do this in the cloud just to avoid downloading loads of stuff. But you could do all of this locally. You could play with all of this locally. I don't. I use machines in the cloud because I'm an Apple person from the olden days and always have been. And so I just like my MacBook. But what we will do in order to get going is we have this platform called Brev. So if you go to brev.nvidia.com, it will ask you to register. Right? It will ask you to sign up for some account. It'll probably send you an email. You probably have to click a link. And you'll get to this point. So whilst you're doing that, I will tell you a bit about what Brev is and why we're going to use it. But yeah, your action now is to go to brev.nvidia.com and go and register. When you get through to this like GPU instances page, that's the place to stop. So we kind of are aware that going and getting VMs from the cloud world can be like a non-trivial thing. And so Brev is like this nice little tool that walks you through and holds your hand through spinning up VMs and kind of doing various things with a machine. It gives you a lot of visibility into what's running and how much it's costing and that kind of stuff. Now this is like a reselling service, so we don't have any GPU. We're not providing like a cloud. Like this is all backed by AWS or Google Cloud or whoever. It's actually all of them. And you put credit into Brev, you go and top up your account, it's like a pay-as-you-go kind of thing, you put some money in your account, and then you can go and spin up a VM on whatever cloud it is. NVIDIA will provision the machine and handle kind of wiring everything through to you, so it will make sure you can SSH to it, it will make sure you've got Jupyter running and you can access notebooks on it, and it will make sure that you can open VS Code remotely on it. And there's like a little command line tool that makes all of this kind of nice and pleasant and easy. And so it's kind of trying to make it a bit easier to do all of this stuff without having to go and become like a cloud expert in whichever of your preferred vendors are. Now, what I'm going to do is tell you a bit about the billing. So you can see I'm in an account here that's got like a few $100s or something we can like magically top up. But when you log in and you get to this screen, once you've registered, there is a tab that says billing. And if you click on that, there should be some button there that says like redeem code under the billing portal. So you don't need to actually like put any credit card details in or anything. Just go and sign up. Make sure that there is like an organization in the top corner. Mine says NVIDIA Pi Data, which is just a group that I work in. You should get some random string of numbers appear in that thing in the corner, but one of the Brev people told me there's a bug where sometimes it says undefined. So if it says undefined, please shout, and we'll fix yours. Brev's quite new, but it's cool. So if you come in, you click on billing, make sure, this little screenshot here says like NCA and then some numbers, right? That's the org that it's in. And there's a button that should say redeem code. And if you put EuroSciPi 2025 into that box, it should credit you with $3, which I know is probably not the most generous gift you've had recently, but it's enough to get us going and enough to get us through the rest of the tutorial and probably give you a bit of time to play with this at home as well. So if you can go through, get registered, and then get to a point where it says $3 in the top right-hand corner, that will get you to this stage where we can launch something and do something. Yeah, okay. Let's do some hands. Who here has got all the way to the end? Some. Okay, who here is struggling to register? Have we got everybody registered? Okay, everybody seems to be registered. That's good. And so you're working through the billing bit, so that's cool. I'll give you a few more seconds to put in the billing things. Did anybody get undefined or any weird behavior from the org bit? You did get undefined in the top.
Yes, but I just put a random name and it works.
Yes, yeah, so the fix is like you click it and you say like create an org and then you match the keyboard and then you click OK and everything's fine. So, cool, okay. What I'll do, as you're all kind of going through, putting the credit in, I'll keep going. So the next thing we're going to do is we're going to launch a VM. Right? We're just going to pick one of the standard out-of-the-box things. So what I need you to do, the instructions are on this gist, but I'm going to click up here where it says GPUs, and I'm going to click Create New Instance. And the way Brev works is it's like a GPU, this is an NVIDIA product, right? So it's a GPU first thing. It says like, which GPU would you like? And you go, I've never heard of any of these random numbers you're telling me. I don't know which one to pick. So what I'll tell you is the L4 or the T4 are like the cheapest ones. So we'll pick one of those in order to keep going with this. I'm going to pick an L4 because it's like slightly more modern, costs like 85 cents an hour, and you've got like $3 of credit. If you want to make your credit go like a bit further, you could pick a T4. You'll maybe getting on for twice as much out of that. You could also try and pick like no, you can't. You could pick an A100 and get like 2 hours out of an A100. Like it depends what you want to do and play with. Like these are just different power of GPU, right? The A100 will run more code faster than an L4, but like for what we're doing learning wise, an L4 is fine. So I'm going to click L4, and then I'm going to pick from one of our many providers, right? So you can see here it says like this is provided by Google Cloud, this is provided by AWS. So this is kind of like a marketplace where providers can come and put capacity in. So I would encourage you just to click the cheapest one. It doesn't really matter what you're doing. Maybe in the future you're like, oh, actually I want this one that's got 32 gig of CPU RAM instead of this one that's got 16 gig. There's different configurations, but I would just click the cheapest one. I give it a name. I'm just going to put my name in. I'm going to spell my name correctly, and then I'm going to click deploy. Okay, I didn't change anything about the software. I've left everything on the default Brev options, and we'll explore that in a minute. But basically, Brev gives you an Ubuntu machine with some stuff installed. But what I want to do in the next half hour is talk about like what is installed, what do we get, and why, and what else do we need, and what's missing, and how do I get it, and try to answer those questions. So this is going to take a minute or so to spin up and deploy. There we go. Okay, the machine's running somewhere. You can see it's gone into this like running state with a big green button. There's also this, it says building here, right? Now this building is doing some like post-install actions. So out of the box, the default thing it will do is it will just install Jupyter and run it. and make sure that it's always running in the background, right, for you in the default environment. But there is like a container option, so you can say like, no, when you start, I want you to run this container. This container has Jupyter in it, so like you do that one and give me Jupyter from that environment. So you can kind of bring your own software with you. In RAPIDS, we have a container that has Jupyter and all the RAPIDS libraries and all the things you could possibly want. And so usually when we do things, we go and pick that and launch things. But this is running, this is building. And the next thing it's going to tell you to do is we need to figure out how to connect to this machine. So on my machine, because it knows I'm on a Mac, it's told me to like brew install this Brev command line tool and then authenticate. And I think if I do copy this, it says copy to clipboard when I click it, those stars are actually expanded to some like magic token thing. So I can paste and run that. I ran that before, so I already have the Brev command line installed. But you all will need to authenticate with Brev from here. Whatever your instructions are for your operating system should appear there. And then we get this nice little tool, right, Brev. And what it mainly allows you to do is it allows you to create and stop and delete and whatever these machines from the command line like you would expect. But it also provides you with all of the ways to connect to it. So we have this brev shell command, which is basically just SSH. You just say brev shell, whatever the VM was that I made, and it figures out how to SSH into it and gets you kind of hooked up and connected. We also have brev open, and that will open, if you're a VS Code user, it will open VS Code and do the remote connection thing and follow the SSH tunnel and get you like VS Code into that machine as well. But it just does it in like a one-liner. So it's kind of nice if you like code or cursor or whatever. I think you could do like brev open -- cursor as well if you like cursor. The other thing it will do is because out of the box it will just do Jupyter. You can see it says like this secure links thing. It will proxy Jupyter through on some random URL that it will give you. So by the time it says health unknown at the moment, but when the machine comes all the way up, Jupyter will be running on the machine and it will wire up through the Brev proxy. You can just click through to Jupyter. And I think there's a button up the top here that says Open Notebook. Like that will be clickable shortly. And I think you can like SSH and stuff directly, but I'm going to use the Brev shell to get through. So I've clicked this like copy to clipboard on the Brev shell thing. And now if I go to my terminal or maybe make it smaller. God, typing with a big microphone in your hand is too big, too small, font, okay? Cool. Okay, good. Right, so it will say, like, waiting for instance to be ready. I don't know how long that will think for a second. But this will give me SSH through onto this VM. Still says building here. It's taking a little while to install Jupyter. But okay, it's SSH me through anyway. So I can see I'm on some machine now in the cloud. So let's have a poke around and see what we've got, see what this thing is. So if I go back into my gist, yeah, these are all the instructions. Hopefully we're able to follow through and get to this same point. Let's just have a little look at the machine, the operating system, just out of curiosity. Okay, it's given me Ubuntu 22.04. This is just a vanilla thing. There would have been an option somewhere to pick whatever you kind of want, but out of the box, we'll go with Ubuntu. It seems to be very common in NVIDIA world. Now, when you've used one of these things for the first time, the first question is like, it told me there was a GPU in here. How can I just verify there's a GPU in here? And the easy way to do that is we have this command called NVIDIA SMI. NVIDIA SMI. So I run this. It gives me a bit of a dump out of what's going on my GPU. Now the NVIDIA SMI command, this comes as part of the driver. So I know that I've been able to run this. They've given me drivers out of the box, which is great and helpful. You might end up in a situation where you don't have drivers, right? Usually if you go to AWS or something and you spin up a GPU machine, you'll get an operating system with drivers. But sometimes if you pick an obscure image or maybe you have like a company image or something that you have to use, you might not get drivers or you might not get the right thing. You'll run NVIDIA SMI, it will fail. You then need to go and install the drivers. If you Google, how do I install NVIDIA drivers on Ubuntu, you'll get like 30 different articles with 30 different methods. Pick one, I'm sure it'll be fine. Realistically though, I would use like whatever the operating system provides. So Ubuntu has this like Ubuntu drivers package. You can just run like Ubuntu drivers and it will say, there's a GPU, I'm going to install the NVIDIA driver. use whatever your operating system recommends. But on Brev, it's given us a nice base image that's got NVIDIA SMI and everything installed. So we can see we have, driver 570 or whatever. We can see a CUDA version here. It's saying we've got CUDA version 12.8. This is just saying this is the version of CUDA that the driver supports. So hooking through the device, through the Linux kernel to user land, we've got support for CUDA 12.8. That's something we need to take note of and pay attention to. We can also see here it's listing our GPUs. So it says there's a GPU of index 0, and it's an NVIDIA L4, and it's using some power, and it has some memory, and other kind of useful stats and information. And it also gives us a bit of a PS output, so it's showing us what processes are running and using the GPU. Now at the moment, there are none, but this is kind of where you can come in and find out more information about what's using the GPU, how many processes have I got running, that kind of thing. So NVIDIA SMI is your go-to, poke the thing, is it alive, is it working? Now, I mentioned CUDA. Actually, I'm going to stop before I go on. Has everybody got a VM? Are people, put your hand up if you're at the point where you're in a shell, able to poke around like I am. Put your hand up if you're not and sad about it. I know some people are just watching, and that's fine. If you need some, are you all right, Sebastian, to go and give people some help? Cool. Okay. If you need help, keep your hand up. Sebastian will come and give you a nudge. I'm going to keep going and plodding through things. Like I said, we'll never get to the end of this, so I encourage you to keep going. But we have NVIDIA drivers, and we have things wired up from the CUDA side. And this tends to be where people, this is where knowledge gets slightly more challenging, because there's a whole bunch of stuff you can go and learn and figure out and understand about all this software stack. And my goal of this tutorial is to give you enough information now so that you can understand what's missing, right? If your end goal is I want to run that number notebook that we just did, in this machine, what do I need to do to get from here to running that notebook? Or I want to install PyTorch and do a PyTorch thing, or whatever, right? How do I go from here to there? How do I debug this? How do I identify what's missing? And how do I see what's going on? So we've got NVIDIA SMI. We can see that. That's great. Now, often when you install things, you will need low-level libraries, right? These are kind of the equivalent of the C libraries that everything depends on in your operating system, very basic pre-compiled code that should just exist, and everything else will dynamically link against it, right? So all of these things you want, PyTorch or whatever, will be dynamically linking against low-level CUDA libraries that are provided by NVIDIA. These usually always live in this place called user local CUDA, and if I do ls-ld, it will tell me you don't have any CUDA libraries, right? So this base Brev image, it's given me a driver, but it hasn't given me a development environment. It hasn't given me any kind of compilers. It hasn't given me any build tools. It hasn't given me anything beyond the very, very basics. And I kind of did that on purpose because I want to show you all this stuff. But if our end goal is I want to be in Python writing Python code, there's kind of two paths that you're going to go off on, right? You're going to go off on the Conda path, or you're going to go off on the pip path. Right, put your hands up if you use Conda day-to-day regularly for managing your software environments. And put your hands up if you use UV or pip or something in that world, poetry or something. Okay, good mix. Right, let's do both then. If you go to, we're having a conversation at lunchtime. If you go to PyData or some of these other meetups, some people never heard of Conda, and then you come to other meetups and they're like, why would I use anything but Conda? So let's do both. So let's start with the hard one. Let's start with pip, right? Pip is Conda exists for a reason. It's because pip is slightly deficient in ways that is getting better all the time, and we're working on it in a good direction. But there's challenges with using pip when it comes to mixing pure Python code with compiled code. And I think in this world of fancy Rust packages and CUDA and whatever, this divide is it's not just NumPy and SciPy and scikit-learn and things that are feeling the pain of all these compiled dependencies now. I think it's getting more and more so. So things are getting fixed, it's all good. But what we need to do for pip is we need to get all of the dependent libraries from the CUDA ecosystem, and we need to put them on the machine. Now, Conda will do this for you, and we can have a look at Conda as well. But I'm going to just copy this big lump here, which is going to do an apt update from the NVIDIA registry, and then it's going to do it's very, very white. It's going to do apt get install CUDA toolkit 12.8. Right? And I've specifically chosen CUDA Toolkit 12.8 because my CUDA version here says 12.8. Right? So you have to pick like the corresponding name. And I'm going to run this, and then it's going to think about this for a while, because this is like the big blanket command of just like, give me all the things NVIDIA has ever written for CUDA, low-level packages. It's going to install a load of stuff. But we have to do this because pip can't handle doing this, right? Like if PyTorch needs one of these things, pip doesn't know where to get that from, and so we either need to know exactly what PyTorch needs, or we just get everything. Right, and usually most people just get everything. So that's what I'm going to do. Some of this stuff's heavy. It's going to take a little while to download. This is why I said don't do it on your laptop if you've got a GPU, because the cloud ones have got big fat pipes and stuff. Question?
A quick question. What are the pip package called NVIDIA CUDA runtimes?
I mean, that has some stuff in it. It's nuanced, and we can talk about it because it's interesting. We're like working in a direction of pip providing all of these things. We're in like a slight challenge in that pip can't actually figure out, like I just said, I need to look at what NVIDIA SMI said and then install the right package. Like pip can't do that. Like pip is just, it's not able to look at your machine and say like, what are you? It just goes and finds stuff. Whereas Conda can. Conda has this concept of virtual packages where it can say what version of CUDA is installed, even though like you can't install the driver from Conda. Conda can still query the version of the driver through this virtual package mechanism, which is super cool. There's a thing coming in pip, in the PyPI world, called Wheel Next. If you're interested in this topic, go and have a read about Wheel Next. But the idea is adding like install time packages that can do this inspection of your system and then decide what package you need. So like when you pip install something, it would say like, okay, what's the thing? Does it have any install time dependencies? Yes, it needs the which version of CUDA have I got package. It installs that, runs it, gets the answer, and then feeds that back into the actual like which version of PyTorch do I need kind of conversation, right? And so that's not like formalized in a PEP or anything yet, but like it's coming. But you'll find on PyPI packages where we've been experimenting and figuring out like what's the future going to look like in pip world. You can pip install these things. It will give you some stuff. Getting it into like a working state is still challenging though because of the pip machinery at the moment.
A question, will it work if you magically guess the right version?
Yeah. If you get it right, and there is it does say it in the thing, if you scroll down, there is an experimental build of UV which can work out the right version. They've like implemented the Wheel Next stuff, even though it's not formalized yet, just to see, and it's cool, it's interesting. So I would encourage you to have a look. But we're getting there with this stuff. Go for it.
Yeah, I have a question about what is already installed in the driver. So when you write NVIDIA SMI, there is a CUDA version 12.8, and then you still install the runtimes. So what is already installed in the drivers and what it uses?
So what's already installed is the extensions to the Linux kernel that are needed to talk to the hardware, right? So very, very low level code execution. You can work against those directly. Like if you're writing some C++ code, you can use the driver. You can call the driver with the CUDA 12.8 API, right? And that will work. But realistically, you don't want to write CUDA code that low level, right? It's like me saying to you, like, you write some assembly. If you're trying to do something in Python, like you're going to start from assembly and work your way up. Like you don't want to be that low down. You don't want to be writing Linux syscalls, right, in your code. Really, you want to be building on top of like libc or musl or like some, if you're writing some C code, you want like a standard library that's got like a whole bunch of functionality that's going to give you useful stuff. This is kind of what we're installing now. So these are like core libc style packages, but also what else? What have we got in here? There's like libcuBLAS, right? So any linear algebra stuff we want to do, right? We need a BLAS library. Let's get the BLAS library. There's cuFile. I want to open files on the GPU. I want the GPU to be able to read from a hard drive without the CPU being an intermediary. Like let's have an API called cuFile. cuSolver does the same kind of thing. cuRand, I want to generate random numbers. Like these things are not provided by the hardware. We need a library to facilitate that kind of thing. So these are the libraries we're providing. They don't ship with the driver because you don't need all of these for your application, right? This is kind of, we're going in like the heaviest way because pip we just can't, pip doesn't know what it needs. So we're just going to install all of the things, right? But I'm downloading like 10 gig of stuff now that maybe I don't want. If I'm building a Docker container, I don't want 10 gig of random stuff, right? Like, but for now, for a tutorial, it's fine. Let's just install CUDA Toolkit. We'll be okay. Go for it.
Question. So, for example, if you install Torch, how will it know whether to take something from your system or from a zip package or something very specific? I think it comes with something added to the path as a relative thing.
Yeah, I mean, it will find these packages. It will look for these packages. If it can't find them, we will get an import error. You'll get some, I can't find this blah, 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 .so file. Right? If you've done any GPU stuff, it's a very familiar error message of like, I can't find libcuda.rt.so or whatever, right? Because it's not provided by these things. Torch have gone, because they're not NVIDIA, so they've done stuff their way. We've done stuff our way. Their way is like better in some ways, and our way is better in some ways. And this is why WheelNext is trying to, like, WheelNext is a collaboration between like NVIDIA, Meta, like a bunch of folks in the Python community trying to figure out like how to do this stuff better. Like Torch do bundle more things than other ways of doing things. Sometimes it means that like Torch is massive when you install it. It's because they've like bundled in a bunch of stuff. And if you go and look at their install instructions, they use different PyPI registries that they host to let you choose the right version. So you just install Torch, but you install it from the like CUDA 12.8 PyPI flavor, right? Which is like they're just trying to work around the fact that pip doesn't know what CUDA is, right? And so like they've done it that way. We've added, if you install ours, you do like pip install QDF-Q12, and we don't pin to like a minor version. You can use any minor version, whereas they do. So like everybody's going to solve this in different ways. I'm trying to like give you like a bit of a fundamental of like all the pieces. We can talk a bit about the various solutions. It's interesting to talk about WheelNext and like how this is going to be less painful in the future. But yeah, it's all a big moving target at the moment. Cool, okay. So I've installed CUDA Toolkit. So if I now do my ls thing that I had before, which is user local CUDA, it should tell me now, okay, I have CUDA. I have all the CUDA standard libraries. They're hanging out at user local CUDA. Now, the next thing I'm going to do, now I have Python, right, on here. This is just, if I just do which Python. I don't have any exciting Pythons. I just have the system Python at the moment. You know, don't use it because you shouldn't use it, but I'm going to use it just to show you how it works. But also, this is the Python that the Jupyter is running in. So when Brev started this up and it started Jupyter, it started it in here instead of creating a virtual environment for some reason. But I can do pip install QDF. So let's say we want the pandas plugin, right? I'm going to install QDF. You can see at the moment we're specifying an extra index URL. That's partly just because our packages are massive and we're taking the brunt of the download bandwidth instead of pushing all that off into PyPI. They also have like upload limits on how big packages can be, and we're always up against those because GPU packages are massive sometimes. But I'm going to pip install QDF. I have to specify a different index, and I have to say which flavor of CUDA I'm on CUDA 12. But if I pip install this, it's now going to go and find QDF and a whole load of other stuff. So it's going to pull down some C++ code, right? It's pulling down libqdf, right? This is a C++ library for data frame, low-level data frame operations. It's going to pull in mjitling, RMM. RMM is like our memory manager for managing memory pages. It's pulled in this CUDA runtime Q12 package, which I think is maybe the one you asked about before. These are providing some like the Python side stuff that's going to hook up to the CUDA toolkit stuff that we've just installed from apt. And so these are like the various layers you need. Right? You need your driver, you need your CUDA, your low-level CUDA libraries, and then you need your Python CUDA library. And you get those from different places, unfortunately. Conda solves a bunch of this in that it can give you more than pip can, but it's not. You still need to, it's helpful to be aware of all these things, I guess. So I installed that. So if I now do Python 3, and I import QDF, hopefully I don't get an import error. No, good. Right, it found all the libraries. That's always the first smoke test of like, can I import the thing, or am I going to get some weird I can't find this compiled code stuff? And if I do this QDF, if I just make a series, right? This is just a, this is like making a pandas series. I'm just going to make it with QDF. That worked, okay? So like that's the other thing. I've now called a piece of code that ran on the GPU and it allocated memory on the GPU. So like that's as a smoke test, it's good. Like I've managed to install all the things successfully. And I think if I just, let me just shove that into the background a second. If I do NVIDIA SMI, we should now see under processes, there is a Python 3 process that is using the GPU because we imported QDF and did something, and it's using 186 meg of GPU memory. I know I made a series with like 4 things in it, but it has to like set up some scratch space and allocate some buffers and whatever. You end up with like some amount of memory used. So that was it, right? We went from like a bare machine, had a driver, we installed CUDA toolkit, we pip installed a Python library that can use the GPU, and then we ran like a tiny little bit of GPU code. You could now pip install PyTorch, you could pip install other RAPIDS libraries, you could have CuPy if you want to do NumPy type stuff. Like there's all these different libraries now that we can access via pip that will leverage these lower level things. Now, let's talk about Conda a little bit for a second. Let me actually check the time. Okay, we've got like 5 minutes left, which is cool. But I want to make sure you've got time for like questions and stuff. But we're at the point where we've got like a working environment. That's great. Conda, we can skip all of the like apt install CUDA toolkit stuff, right? Because Conda can solve for CUDA as well, because Conda is like not just a Python thing. And so it means we can do something like this, right? We can install Conda if we want to. And we can do, create a new environment from our, Conda Forge and NVIDIA channels. We're going to install QDF with Python. We're just going to pin our CUDA version. I don't think this is actually necessary. I copied this out of our documentation, but I think you can omit this. I think they're just being belt and braces with which CUDA versions you want. But when you install this, it's looking for QDF. And so go, okay, well, QDF needs libqdf and all those other things that pip pulled in. But then I say, okay, well, libqdf needs CUDA-RT or like some of these other low-level CUDA libraries. Those are also packaged and on Conda Forge and available like through that mechanism. You don't need to apt install them. So Conda will solve that. Pixie will solve, whatever your favorite way of doing Conda stuff is. They will solve that. They will pull in those things. So you only need the driver. Right? You need a machine, you need the driver installed, and then Conda or Pixie can do everything else. So it's quite like it's a more holistic approach. It's how we build containers typically in our community as well, because you just want the minimum subset of packages in there, right? Like I just want the libraries I'm going to use and just their dependencies. I don't want to be pulling in all of CUDA toolkit and all of this and all of that. So we just use Conda for creating those. And Conda can solve all of that. And you would run the same thing and get to that same point. So, yeah, go for it.
You were pulling additional channels, but it looks like the packages are for the most part available in Conda Forge. Is there something wrong with using the Conda Forge packages?
I think there's just a couple of things. We're trying to get away from these channels and get everything into Conda Forge. And it's been like a slow progress. But yeah, it's like most of this stuff should be being pulled from Conda Forge. If you look at the solve, it almost all comes from Conda Forge.
I think QDF itself is not Conda Forge, but most of the other stuff.
Yeah, I think that's right. Cool. Okay. So there's a bunch more stuff in here. A lot of it more we can like dig into for like a couple of minutes is. Once I'm at this point, I've installed some software. I now know enough like programming in Python that I can run some code that's going to run on the GPU. I can be dangerous now and go and do things. Like, what next? Like, how do I actually like explore this stuff and debug it? And like, what do I need to know beyond normal Python things? Like, all the normal Python rules apply to writing and debugging your code and exploring what's going on. But what happens if you write some code and you run it and it takes a long time and you're like, well, what? Is it using the GPU? Like how much GPU, percentage am I using, utilization, how much memory am I using? Like, is data being copied back and forth between them? Like, how do I get the visibility, especially if I'm at the top level using these really high level libraries and I run it and the performance, is not what I expect it to be? Like, how do I see? How do I explore this stuff? So there's like a whole bunch of tools for doing this. NVIDIA SMI is like your first entry point into all of these things. There's different subcommands. I put a few examples in here. NVIDIA SMI-Q just like buffs everything it knows about everything in the world out. So you can kind of have a look through that and see like, what does NVIDIA SMI know? It knows a lot. But then beyond that, there's a few things. There's NVIDIA SMI under the hood uses this interface called MVML, which is just like a metrics querier for the device. There are Python bindings to that, so if you want to write your own little tool that just tracks these things, you can. There's a notebook in the tutorials I linked at the beginning that talks through doing that. We have this package called NVIDIA MLPy, which confusingly you import as PyMVML, because I don't know why. I do, there's history and exciting beef, but but one of the things that we built with that is there's this library called JupyterLab MV Dashboard. This is a plugin for JupyterLab, which just exposes all of that stuff up into the JupyterLab UI. I'm actually gonna, I think I can do it. I didn't do any conda stuff, so it shouldn't get in the way. I'm just gonna pip install JupyterLab MV Dashboard. And I'm just gonna restart the Jupyter that came out of the Brev box. And then I think if I go to Brev and click Open Notebook, and open Jupyter, you see there's like a little GPU over on the left-hand side here. And if you click that, it gives you these options of all these different graphs, right? So you've got like GPU memory usage, like how much memory am I using? GPU utilization, what percentage of the GPU am I using? All sorts of other graphs and exciting things. It will show you like CPU stuff as well if you want to see all sorts of other. This is a bit like Task Manager or Activity Monitor or whatever in whichever operating system you like to use. But it gives you a bit of insight into, okay, I've run my code in my notebook. I think it's using the GPU. I'm going to look at this. GPU utilization is not doing anything, so I think something's gone wrong. Like, this is a good place to kind of come in and get at least a bit of an insight into what is running. And you can see you've got these like PCIe throughput. That, remember the PCIe connection inside the machine is how the GPU is talking to the main system. So if this is high, that means there's like lots and lots of memory being copied back and forth, lots. So there's all sorts of different tools you can use in here to look at things. I think my claim to fame is I drew that GPU icon. It's my one bit of graphic design I ever did, is I made that GPU. Okay. The rest of the notebook, we are at time, so I don't want to keep you because you're going to need to go to the next thing. But the rest of this shows you like some command line monitoring things, shows you some of the built-in profilers we have in our tools, and it gets down into like Nsight, which is our like debugging tool that gives you like full-on traces of how we execute code. But this came with the big fat CUDA toolkit thing, right? So you can do like nsys profile, bunch of flags, and then like Python my script, and it runs your code and then dumps out like this big profile that will give you like flame graphs and all sorts of things that you can open either in the Jupyter Nsight extension, or there's like an Nsight desktop client as well. There's even a Mac version. You obviously can't run the code on the Mac, but you can look at the profiler front end on the Mac and whatever. So yeah, I encourage you, please do continue to work your way through this material. Maybe there should be a 4-hour SciPy tutorial because there's way deeper rabbit holes we can go down. If you want stickers, come and get stickers. Please use your credit, please use the rest of the notebooks. And yeah, I'll be around the rest of the week, so if you have any more questions or you want to dig into any of this stuff, let me know. And thanks for hanging out. If you want to keep the credit, by the way, like go and delete the thing. Otherwise, like that machine will keep burning, and then your $3 will disappear. So go and delete that. I started one yesterday, and then got on the plane and forgot about it until just before this session, and I was like, oh no, that was $24 of stuff. So yeah, don't do that.
I'll grab a sticker.
Oh yeah. I think I've got NVIDIA.
Oh, that would be cool. Awesome. So I'll grab also one for my friend.
Yeah, go for it.
Thank you. Yeah, my friend is just very. He loves CUDA and programming and stuff. So he'll be happy.
Really enjoyed the talk. I'm just curious about QPy because
Yeah.
I've heard about it, but like
Yes.
I guess my main interest is integration of kind of array processing, so X-array.
Yeah.
And I know that you can use QPy as a backend, so I was just wondering how that relates to all the CUDA stuff.
I mean, QPy is like a re-implementation of NumPy in CUDA, right? So
Okay.
like the Python front end is the same.
Yeah.
You can almost do like import QPy as NP and then
And do
crack
everything the
on.
same.
There's like two things that you can't do.
Right.
One of them is you can't do numpy.asArray on a QPy array. It will shout at you and say, "Don't accidentally copy this to the CPU," which we spent ages fixing bugs in X-Array around that.
Oh right, okay.
Because X-Array was trying to coerce integers into arrays, right? So into like scalar.
And it was doing as arrays and
it was doing
accidentally.
as arrays and accidentally pulling GPU arrays back into the CPU.
Okay.
So there's nuance, but yeah, it's basically a one-to-one mapping between the two, and it's just for some operations. You think doing like a mean on a parallel processor is
So much faster.
insanely faster than doing it on a CPU.
Yeah.
So like cp.mean is way faster than mp.mean.
Okay.
And there's other parts of linear algebra that are not as parallelizable, but you can get a lot of benefit out of doing it.
Right.
If you're interested, I can show you some code.
So I'm curious how this will next. I saw there was a prototype experimental working, but it sort of looks like there's no plan to make it stable.
I wrote it like
that.
Well, I mean, I don't think UV has a plan because they're waiting for NVIDIA and Meta and everyone to like write the PEP, I guess, and then get the Python Steering Council to approve the PEP, and then do it. So it's.
So would you say it's something that's going, let's say, next year?
Yeah, is that kind of next year, the year after, maybe? I don't know. It depends how long. It depends how long it takes to get approved.
extra classes where you need to
So yeah,
do
it's
some
been there for a while, right?
Yeah, I think so.
So from where you see
Yeah, looks like it's not going to get
NumPy array,
stable soon.
QPy array.
Yeah, but
No.
I know what's the
Yeah, no, they had a conference recently, the Wheel Next Summit. So like, there's people that care, and it's happening. It's trying to do it in a way that everybody's happy with. Do you know what I mean?
Yeah.
So it's
quite slow.
yeah, exactly.
Nice. Interesting.
Good. Good. I'm glad. There's a lot to CUDA. Do you know what I mean? And it's easy to get overwhelmed by how much there is to possibly learn, but like equally you can get going with just knowing some fundamentals.
But people are using this mainly because the speed, right?
Yeah.
And you don't your Mac doesn't have a GPU?
No.
Oh, me neither. But the new ones have, right?
They don't have GPUs that can run CUDA code. Right?
Oh,
They only have
so
Apple and
they don't
Silicon.
work. It's not working.
None of this stuff will work on a Mac.
Okay.
Even one with like an Apple GPU, because it's not the same.
Okay.
It's not the same class of performance. Like a lot of libraries like PyTorch and stuff. They will implement like a CUDA backend and like an Apple Metal backend, and so you can get some performance, right? Like, but it's when you want to run stuff in production, you go and get an NVIDIA server and you run that on the cloud. And so I think a lot of people like to develop on like a small NVIDIA machine and then deploy to a large NVIDIA machine so that lift is easy. Do you know what I mean? Whereas if you develop on a MacBook and then deploy to a large NVIDIA machine, it's like it can be a bigger step, right? Different bug class than if you develop on an NVIDIA machine.
Oh, so, for example, it's been a lot of I don't know, they're not exporting the GPUs to China for the DeepSeek training, but how fast are those GPUs that are being able to export?
I mean, I can't remember the numbers off the top of my head. They're not like the top tier performance. They're like slightly behind. I think it's whatever the US government says is like the maximum performance. I think they just like tune them to be like right on the line, you know. So I don't know. I don't keep up to date with where that line is, though, you know.
But because they were, have you read the papers? Because they were able to train their model in a very efficient way, you know, right?
They did, yeah. They trained it very efficiently. Yeah, it was good. The DeepSeek stuff was really interesting.
Oh, okay.
But like, I don't know. That was.
A few months.
Just the next. No, but it's just like the next step, isn't it? It's like, oh, what can we optimize? What can we? Because then we can train more models. We can train bigger models. Like it's the amount of compute that we use never goes down, right? Like when you start doing something more efficiently, you do more of it, and so.
Wow.
There's always demand for NVIDIA stuff, which is good for us, I guess.
Yeah. Yeah. Very good. Great. Thank you.
Yeah. No worries.
Thank you.
Thanks for coming.
Thank you.
Nice case is so much faster than this. I don't know if with Python, I mean, very good frameworks, Microsoft Magic, they use high specializations.